Hello everyone, welcome to this session. My name is Chikaya Naik and I'm the Senior Director of Engineering at Pluribus Networks. Today we are going to cover controllerless open SDN fabric for Telco Edge. We will share some of the best practices that we learned as we deploy the distributed cloud. We will also talk about a few innovations in the distributed cloud. So let's go ahead and get started. If you look at today, how the public clouds or the large public clouds are deployed, you will see they are largely deployed in huge data centers that are located at small geographies. Additionally, they are operated using automated data center network solutions that are specifically designed for this type of architecture. However, new set of applications, primarily in the telco space, have come up that require not a centralized cloud, but more of a distributed model for deployment of the cloud, more towards the edge of the network, which means that the compute, storage, and networking equipment has to be moved towards these locations, which includes central office, 4G, 5G base stations, remote field, and on-premises. So what does this mean? It provides a huge opportunity for telcos and other owners of beachfront real estate properties to capitalize on this transition. So let's look at some of the challenges that we face today as you deploy the distributed cloud at the edge. The current solutions that are deployed for the centralized data centers or the centralized clouds do not lend very well for the distributed cloud. For the distributed cloud, we need to build purpose-built solutions in order to meet the requirements of the applications and endpoints that would like to use the network. So what are some of those requirements? One of them is requirement to have very low latency for these distributed architecture or distributed apps that require these low latencies. Additionally, there will be constraints in these locations, like closer towards base station, wherein space is a constraint, as well as power requirements are very difficult to be met compared to the large data centers where space and power are available in plenty. Also, for business reasons, the cost of these distributed cloud equipment has to be kept to a minimal. In order to support the same, in order to support multiple tenants, we need to not just have a small form of slicing of the network, but to be able to have a deep slicing in order to support multiple tenants in a smaller form factor. So we will look at more into these requirements in the subsequent slides. So stepping back and taking a look where we stand today in terms of the distributed cloud or the edge deployments. So today we have large centralized data centers, or in the public cloud, we have switches that are networking switches that are deployed in the data center that deploy a leaf spine architecture. In addition to that, at the edge of the network, you would have a border leaf that connects to the next hop, which will act like a DC gateway that provides the north-south connectivity. So this has started moving from just the centralized location to regional data centers as well as co-locations in order to meet the SLAs that the newer applications require. So what are some of these new apps that are coming in that require this low latency and other requirements that's putting on the network infrastructure? Some of these are called out here, include like 5G phones, IoT, self-driving cars, 3D gaming, and many more. So these distributed applications do require low latency and face some challenges when they have to backhaul all the way to the centralized data center, as the latency or the round trip time in order to exchange some of the messages can be larger. So typical round trip times for the regional data centers or co-locations from these endpoints are in the range of 20 to 50 milliseconds, but these apps would like that to be to be much lower. So what that means is that this model has to evolve further in order to reduce the latency of the round trip time for these apps to reach towards towards the backhaul and be able to communicate amongst themselves. So the model, as it has evolved, you have more of the equipment, the compute, storage, and network equipment has been moved to central offices, as well as more closer towards the towers, as in the base station, also called as the deep edge. So this will help to, as the endpoints are more closer towards the base stations, it minimizes the latency. But we have to address the concerns on space and cost concerns of equipment that will be deployed in these space-constrained base stations as well as the central offices. Typically, the real estate only allows about 2 to 6 switches to be present in this in such constrained environments. Next, we'll briefly talk about how would the network deployment look like in order to support this distributed cloud. Can a model that was deployed in the centralized data center, which was basically your leaf and spine that are connected together to form a pod, can similar model be used for distributed cloud as well? So one of the best practices that we had looked at is to be able to connect the switches from a central office towards the base station. You connect them as a single pod or a fabric that can continue to be managed or orchestrated by a controller like a Red Hat OpenStack controller or others that are available there. Similar such pods can be available in different geographic locations. What these pods would hold is the ability to have resources for specific tenants, and the tenants could now span not just within one pod but across pods as well. So we need to have ability to connect these pods together so the tenant traffic for one tenant stays is isolated from other tenants, but at the same time they're able to communicate amongst the resources that are allocated to that tenant. In order to have this interpod communication, we can use standards-based protocols like EVPN and federate it amongst these pods or fabrics. And then they could be orchestrated by or some orchestration tools that are available. That way you can build a giant fabric that will allow for multiple tenants to be supported, as well as allow mobility all the way from public cloud to the edges of the network. Next, we will talk about what are some of the other requirements from a software perspective in order to meet the requirements of this distributed cloud. One of them is deep network slicing. When we say deep network slicing, we mean that you can have multiple tenants that are crammed up into the available hardware resources available. So you can share the available hardware among multiple tenants, and if you can put more of them into a single box or a small set of boxes, then you'll have a more scalable solution. In terms of slicing, we have to slice them into three different, we have to look at slicing in three different planes. In the data plane, where the packets get forwarded. In the control plane, whatever protocols, routing protocols, how they are utilized. So traffic for one tenant is isolated from the traffic for another tenant, as well as from a management plane perspective. So from a management plane perspective, one tenant should be able to see the resources only that are dedicated or allocated to that for that particular tenant. We call this notion as a VNet. So particular tenant will be able to see and provision only the resources that are allocated by the overall administrator of this fabric, who is a fabric admin. What the fabric admin has allocated, only those resources the network the VNet admin will be able to provision for the resources that are allocated to him. So this network slicing would allow fairness for resources that are allocated to a tenant, as well as meet the SLAs for tenancy. In a data plane perspective, the hardware like merchant silicons from Broadcom and others provide ability to carve out the data plane using the notion of virtual forwarding instances, or VRFs. And from a control plane perspective, VRFs are also supported in the control plane, and you can have a BGP session on a per tenant basis or per VRF basis. So this way, the resources in the overall fabric can be carved out on a per tenant basis and can optimally be used. So this is one of the functionality that's available in large data centers, but can be used more optimally in for distributed cloud as well. Next, let's look at the hardware components that can be used for networking of for the distributed cloud. So there are multiple white box solutions that are available, some that are OCP compliant, others that are not, or in the process of or getting accepted for OCP, that you can use for building the distributed cloud. A couple of them are shown over here. There are a lot more that are available there. You can get the general list from the OCP website. They come with the different form factors, as well as the compute storage capacities. Also in terms of the forwarding capacities from Broadcom, there are ASICs that can store larger table sizes than the prior generations. So, for example, the Broadcom Trident 3 has a lot more bigger capacities, can store multiple VRFs that are much more powerful than the prior generations. Similarly, from a compute perspective, if you throw more capacity at it, like the Intel 12 core CPU, then you can get better performance, and you can have, in the smaller form factor, you can load multiple applications as well as support multiple tenants. So ideally, some of the common elements that are needed for the distributed cloud and the applications that that would use them. It's good to have 32 gig of RAM and 512 gig SSDs, but that's just a recommendation from us. Now, if you look at the next generation of the white box switch architecture, there can be certain optimizations that can be done. Traditionally, the switching ASIC would be connected over PCIe to a multi-core x86, which would provide the CPU module and would have storage and associated with it. But in terms of being able, since there is you have more powerful computes available, if you can have two additional 10 gig links that directly connect the switch ASIC to the multi-core CPU, then you will have ability to host additional applications which can use that bandwidth, like firewalls, offloading of IPsec, or run better analytics. So those are some of the things that are coming up with the next generation of white box switching architectures that are becoming available, along with the newer ASICs like Trident 3 and Trident 4, Tomahawk 2, and so on and so forth. Lastly, let's look at any further innovations that we can look at in order to better utilize space, power, and cost efficiencies. So we talked earlier about, in large data centers, you have the DC gateway that provides north-south connectivity. These tend to be very expensive boxes, and that typically sit at the edge and make it cost prohibitive. So an improvement that you can do is that move those functionality from those expensive boxes to white boxes that are OCP compliant, and can still hold up to a large number of routes, table sizes, and have decent amount of compute and storage capabilities. And they come with 1/5 of the cost. So that's an innovation that can be looked at. Additionally, not only have a separate low-cost box for your DC gateway, you could actually merge the DC gateway functionality into your border leaf, and that way eliminate one box from the equation. So in other words, the border leaf itself would have the routing capabilities that would directly talk to your transport network and be able to handle the routes and the requirements of applications that are running at the edge. I remember these the edge deployments would not be as large fabrics as your as a single large data center. They would typically have only 2 to 6 nodes. So integrating the DC gateway into the border leaves makes a lot of sense for these edge deployments, especially at the base station and closer to the towers. So last but not the least, if we quickly summarize what are the three key takeaways that we can take from this presentation. Number one is you can use general purpose hardware from white boxes, especially the next generation, which have more compute, better backend capabilities, as well as better storage capabilities. Those can be used for the distributed cloud. Second, you can have consolidation of some of the devices which tend to be separate for large data centers. For smaller footprint, and better cost efficiencies, they can be combined into a single form factor. And third, in terms of the software that manages this distributed cloud, you can use the concepts that you did, that you learned from leaf spine architecture in large data centers, and deploy them for at a pod level, as well as hook up multiple pods to form a large fabric for the distributed clouds. So with that, I'd like to stop here and point out that if you're interested in collaborating, then drop me an email, or for additional information, check out the Open Compute website. There is specifically a working group for the Telco Edge, and we are looking to partner with the community, or for developing white papers, or for other interesting projects. If you are interested in collaborating, then reach out to me. Thank you very much. Bye bye.